So, good morning. Okay, I have a bit of a cold, so it's still okay. So today I want to talk about applications of freeness and what you learned in last sections about two von Neumann algebras. And in particular I want to talk about compressions of free group vectors. Now really applications. So the first big results for Gillescu and Naikema and Dragulescu. Freeness two von Neumann algebras. Specifically, it's about compressions of free group vectors. Now, free group vectors are von Neumann algebras in clear characteristics. Okay, so let me first make some remarks about compression. What do I mean? This is a way of constructing out of von Neumann algebra, new von Neumann algebra. And maybe first I want to say that our von Neumann algebras are very specific ones because they have a trace and they are living on an infinite dimensional Hilbert space, and so they are what is called a 2-1 factor. I mean, they are vectors, but the word vectors of the Neumann algebra is divided into type 1, 2, 3, and type 2 is subdivided into type 2, 1 and to infinity, and in a sense the nicest, at least for us, are the type 2, 1. So let me just say what it is, and this just means essentially that we have a trace now from Neumann algebra. Von Neumann algebras are vectors. So vector M is called 1. So this goes back to variant von Neumann vector. If it has a trace, but I mean of course also the finite dimensional B of H's have a trace. They are kind of the trivial guys, so they are type 1, so that's not what we want. But we want that it's infinite dimensional. So if M is infinite dimensional and there exists a trace, okay, it should have some continuity, and actually let us say a more continuous trace. How? And we know that they have such a guy for our free group vectors. Okay. And I mean this trace in particular means that we cannot have a B of H for H infinite dimensional because there is no trace on B of H in infinite dimensions. So only if we restrict to sub-von Neumann algebras we have a chance of having a trace. Good. Okay, and maybe we want to non-continuous in the von Neumann algebra context. I mean non-continuous with the C star kind of continuity. In the von Neumann algebra context, we would suppose that probably we should have a normal trace, and this is automatic. And also the trace is unique. So those are basic facts. Just want to recall. Okay, so the trace now is unique. So this is non-continuous. There's a unique non-continuous trace. And if we have such a tau, then it is automatically a normal and also faithful. Normal and faithful. And of course, we know, I mean, the trace which we have in our 2-1 factors, of course, are normal and faithful. But it's only the only possibility for having the trace in those guys. Good. Okay, then, what is the nice thing, or what is about the trace? What does it tell us about von Neumann algebra? And actually, if we can restrict it, of course, to projections, and this then gives a kind of dimension function. I mean, projections correspond, I mean, they are projecting down to a subspace, and then the trace somehow gives us a kind of dimension of the subspace. But all those subspaces in the ordinary sense are infinite dimensional, but we can distinguish in the infinite dimensions between different sizes. Okay, so the trace restricted to projections. And I mean, in our context, projections are always orthogonal projections. And operator setting here is orthogonal projections. The trace is defined on all of M, so in particular on the projections of M. And we know for M has many projections. So restricted to those projections of M gives a kind of dimension equation. And that's actually usually how you show that for type 2-1 you have a trace by first defining a dimension function and then extending to everything. Okay, and this dimension function for type 2-1 vector has the following properties. So one has. So first of all, the values which you can take on are values between 0 and 1, and actually all the values between 0 and 1. Our trace is normalized and the power of 1 is 1. And of course, tau of 0 is 0. And I mean, projection is positive, so tau must be positive. So it must be between 0 and 1, but actually every value between 0 and 1 can be achieved. For all t between 0 and 1, there exist projections t, of course in M, and then we have a call projection. I mean, acting on the Hilbert space, it's an orthogonal projection, projecting down onto a subspace, but of course we can describe it in purely algebraic terms. So the projection is characterized and self-adjoint, and projection means its square is equal to p. Okay, we find such a projection such that the value of p is equal to t. Okay. And of course, in the finite dimensional setting, of course, we don't find this continuity. If I mean b of h is n-dimensional. If I normalize my trace, then I only find multiples of 1 over n as possible values for my projections. But here we are really in a continuous situation. Okay, and furthermore, actually, the value of the trace allows to distinguish, or to check whether projections are equivalent. We have a canonical notion of equivalence between projections, namely that we find partial isometries which move one into the other. The two projections in M are equivalent in the sense of Florian von Neumann. This means I mean, in a Hilbert space setting, they are projecting down to different subspaces, and then I find a partial isometry which maps one subspace to the other in an isometric way. And again, a partial isometry can be given in purely algebraic terms. I did this when we talked about the Roland proposition. So this means we have there is a partial isometry. Partial isometry maps a part of the Hilbert space isometrically to another part, and orthogonal complement goes to 0. So it's an isometric mapping between a subspace here and a subspace here. And in terms of the isometry, the domain and the range are given by u star and by u star u. Also, this means that let's say u star u is equal to p, and u star is equal to q. Also, this means p is mapped to q under dimensionless cube. Okay, and such, so this is the canonical notion of equivalence, and of course it's important that this partial isometry is in M. Because in D of H, you can move any infinite dimensional subspace into any other infinite dimensional subspace. Oh, okay, but this U is not necessarily here in M, and in M we can only move one to the other if they have the same trace. And of course, I mean, because you see they must have the same trace if you have this, because tau, trace property tells us that tau of this is the same as tau of this. Okay, but this is also if and only if, so namely, the projections are equivalent if and only if tau of P is equal to tau of Q. Good. Okay, and so maybe you should think of this as, I mean, tau of P is measuring somehow the size of the subset of the subhilbert space onto which the projection projects down. Of course, in ordinary terms, all those sets are infinite dimensional. Okay, but I mean, if I go to 2, 1, I have a different kind of measure. So I mean, I have the whole space, of course, infinite dimensional space, but this has size 1, and then I have a space which is half the size of the whole space. And I have something which is a quarter of this. Okay, and essentially, up to equivalence, there's only one subspace which has size 1/2 of the whole space. And of course, there's also size 0. Of course, that's just a 0 set, but all finite dimensional subspaces are also equivalent to this. So the finite dimensional ones, they are all like a 0 set. Okay, so this is really measuring somehow the size among all the infinite dimensional subspaces. Tau of P. Measuring relative size of the range of P. So this is, if my polynomial algebra lives on H, D of H, then of course P projects down onto the subspace of H. Measuring the size, and in this sense we have a continuous dimension of all spaces. And thus, continuous dimension. Which can take on all values between 0 and 1. Oh, okay, so this is kind of continuous geometry. Good. Okay. But now, what we want to do is to build new factors out of given ones. And I mean, one possibility, which we have more or less already seen, is if we are building matrices over our von Neumann algebra. So we take the matrices where the entries are coming from the von Neumann algebra, and of course this is a new von Neumann algebra. But we can also go somewhat the other direction, namely we can compress the von Neumann algebra into smaller pieces. Right? We can compress by projections. So this was the general idea, so given to one factor M. New factors. Taking matrices. Over M. So that's something which is easy and which you already have seen. Also for probability spaces. But one can also go the other direction. Direction, and this is called compressing von Neumann algebra M with a projection. So this means I want to see that I can write my von Neumann algebra as matrix over something else. Okay, so let me give you the more precise definition. This. So I consider von Neumann algebra represented on the Hilbert space H, and this should be a 2-1 factor. So we only look at 2-1 factors. Let this be 2-1 factor. And of course, this has a Bedford normal trace, which we call our Bedford normal trace tau. Okay, now I can take the compression. So if I have a projection, so for any projection for projection P, in M of course, I can consider now a compressed space where I just multiply everything from left and right with this P. Also I consider P and P as a set. It's given just by taking elements from M and then multiplying from the left and the right with this P. Okay, and of course, I mean, this is again algebra, and it also has a unit, but the one is of course not the one from here, but the one is not a P. Because if x is 1, now you get here P squared, which is P. So, and this of course corresponds to the unit in this set, because if you multiply with P, nothing changes. Okay, and so I mean, I can also see that this is again a von Neumann algebra. And of course, so the unit is unit P. And this is realized now. I mean, this guy here was realized on H, and if I'm now projecting down here with P, of course I'm only acting on the range of P. So I realize this new von Neumann algebra, or just on a subspace, which is the range of P. Also, this von Neumann algebra is realized on the bounded operators, by bounded operators on this subspace. Okay, and there this is again a 2-1 factor. One factor, and of course, a priori, this depends on the projection. And we have many projections, but we have an equivalence related between the projections, which is given by the trace. And it turns out if you have an equivalence between two projections, you also get an isomorphism between those corresponding one factors. So this means the von Neumann algebra which I get here does not really depend on P, but only on the trace of P, which is a number between 0 and 1. So this is 1 factor, and its isomorphism class depends only on the equivalence class P. Suppose you can imagine if I have a partial isometry which maps P to Q, then you can use this for mapping the projection by P, the compression by P to the compression by Q. Okay, so this von Neumann algebra which you get depends only on the equivalence class of P, but this is described by the trace of P. Only tau of P, and let's say this is T. Okay. And then this equivalence class of von Neumann algebras, also this von Neumann algebra, is usually denoted by n sub T. Class is denoted by m sub T. So we have this for all t between 0 and 1, because we have such projections. And actually, we can now go over also two matrices and extend this. Yeah. But maybe that also, so of course, that, so we call this guy here the compression of M. Those are our compressions, which up to now we have for t between 0 and 1. But if I go to matrices, then I get bigger guys, and in the matrices I can also then compress. So I mean I can essentially do this here for all t positive numbers. Over matrices over M. So let's say M by N matrices with entries from M, and then compressing there with projections, then I can also get T's which are arbitrary. So if I go to the N by N matrices, this essentially corresponds to the fact that T is equal to N. Go over to matrices gives me the possibility of having also integer N's, but then on those guys I can also take projections and only take smaller parts of it, which allows me to get all real numbers for all t bigger than 0. Okay, so by going over to matrices over this and compressing there, projections, one can define M sub t not only for t between 0 and 1, but for all t in R plus. Okay, and maybe we should exclude t equal to 0, because for t equal to 0 we multiply with 0, then this guy here is 0, and then we have an algebra where 0 and 1 is the same, which is not a good thing. So t equal to 0 maybe should be excluded already from this problem. Good, so we get new von Neumann algebras, and those from Neumann algebras, I mean, they might be the original algebra, or they might be different from Neumann algebras. I mean, there are many von Neumann algebras. Some von Neumann algebras are, the class of von Neumann algebras, even of 2 1-factors, is very big. I mean, there's no hope of classifying all of them. So it's really a very big class, and so if we start with this construction for given von Neumann algebra, if we do those compressions, we might get totally different from Neumann algebras, or we might get the same. Okay, the question whether for which t we get the same, this is encoded into what is called the fundamental group for Neumann algebra. So we define subset of the real numbers, namely those positive t's, such that the compression of M by t is isomorphic to the original. Okay, and this of course is a kind of invariant group von Neumann. This was already introduced by Murray von Neumann. Of course, definition is one thing, to calculate this is another thing. Okay, but at least I mean this has some structure. And I mean, we call it a group, and so this is actually a group. It's not just a set of positive numbers, but with respect to multiplication, it's a group. So some marks. Murray von Neumann. For those things. showed that this doing compressions really satisfies some kind of group law with respect to multiplication. So namely, here I have my 2-1 factor, then I compress it by S, then I get another 2-1 factor, which I can then compress by T, and this is the same as compressing directly by S times T. So this is isomorphic to M compressed by S times T. So you see how this group structure comes into the game. And thus, I mean, from this you also see that if I take Mn and I compress it by 1 over n, and this is isomorphic to M1, and M1 is of course M. So you see that Mn is the inverse of doing this. So this means that Mn is really the n by n matrices over n. It's just here, so Mn is really just the n by n matrices over n. Of course, all this fits together. And in particular, this also implies that this f of m really is a multiplicative subgroup of R plus. It's not just an arbitrary set of positive numbers, but it's really a subgroup. And it's called fundamental group. Okay, so continue on the sentence. It's f of m. M is a multiplicative subgroup of the class. That's also a good reason to exclude 0. Okay, and then of course, so we have here abstractly defined some kind of invariant of von Neumann algebra. So you have two von Neumann algebras which are isomorphic. They must have the same fundamental group. But of course, such things are only useful if I really can calculate them for examples. And it's not so easy to calculate this. But actually, Roland von Neumann could do it for the hyperfinite factor. The hyperfinite factor is the nicest 2-1 factor. Roland von Neumann also showed that hyperfinite factor, which we denote by R, this was coming out of the group construction if you use S infinity. That was somehow the nicest von Neumann algebra, about which we know a lot. In particular, for example, we already know since times of Roland von Neumann that in this case, the fundamental group is the maximum possible one, so namely it's all of R plus. So we have that fundamental group of R is R plus. So this means if I take the hyperfinite factor and I do any compression of it, I get again the hyperfinite factor. And this means this also means there are many ways of representing the hyperfinite factor. Good. So, but now we are interested in a different class of von Neumann algebras, namely the free group factor. So the question is, what about the free group factor? What is there for fundamental? Roland von Neumann showed the free group factors are not isomorphic to the hyperfinite factor, but otherwise nothing was known essentially since those times, until Roland started free probability to attend this. So nothing about compressions, anything else of the free group factors. progress in this direction. We introduced free probability for trying for getting to understand the free group factors. Right? Actually, after a while, after free probability was developed for a while and the relation with random matrices was made, he could really show some things. Also now, we know something about the free compressions, and actually, so what we know is that if I take the free group factor on n generators and I compress this with a projection of trace 1 over k, then I get another free group factor, m, where this m of course depends on n and k, like follows, so namely n minus 1 divided by n minus 1 is k squared. So this was the first big result of Roland from 1990 about the free group factors. Okay, and n is here finite. If you read this informally, if n is infinity, then it would say that the compression is an infinity itself. This was not included in the original proof of Roland, but a bit later it was shown by Roland that this is indeed the case. So that this is also true if n is infinity and then also m is infinity, and this means that compressions, at least by 1 over k, give you m infinity again, which means that the fundamental group contains at least the 1 over k's, so it contains at least the rational numbers. So n okay, but the Roland then could strengthen this actually to showing that also for the free group of infinitely many generators we get R plus as the parameter. This is by Roland. Okay, and this was later then refined by Roland and also Ken Dijkema to really get some more information about this. Good. Okay, but what I want to do is I want to show you essentially the proof of this, but to be concrete, I take specific values. So I take n equal to 2 and k equal to 2, and then m is equal to 5. And I want to show how to prove this by using what we have learned about the free group factors by realizing it with semicirculars and such things. The proof I'm doing is works the same for all n k. It's just easier to write down explicitly. Okay, so we will consider, let's say, n equal to 2, k equal to 2. So this means I'm compressing the group factor on 2 generators with a projection of trace 1/2. And then what do I get? N minus 1 is 1, k squared is 4, so n minus 1 should be 4, so m is equal to 5. So this means compressing the free group on 2 generators by trace 1/2 gives me a free group of 5 generators. Like this theorem. Of course, it was done in this general form, but really let me write it in this way. In this specific example, I take the free group on 2 generator, compress it with trace 1/2, then I should see that I get 5 data. And of course, I mean, we know that taking 1/2 compression is inverse to taking a compression by 2, which is going over to 2 by 2 matrices. So we can also write this in a different way by saying that L of F2 is the same as the 2 by 2 matrices over L of F5. Equivalent to saying that L of F2 is given as 2 by 2 matrices, 2 by 2 matrices over L of F5. Okay, and this means, of course, we should start, if you want to show this, by realizing L of F2 via 2 by 2 matrices. But that's actually something which the random matrices gave us some idea for. Because I mean, L of F2 is generated by 2 free semicirculars, let's say, and we already saw how we can realize semicirculars as 2 by 2 matrices. And that's what we are going to do here. Hence, we should realize L of F2 as 2 by 2 matrices. And we talked about this in 9.2, where we realized one semicircle as a 2 by 2 matrix. And of course, we can do this for more generators. So generalizing 2. Also, let's say x1. Also, we need 2 generators, 2 free generators for L of F2, which we want to write as 2 by 2 matrices. Okay. The first generator, a semicircle, we can write as S1, C star S2. Okay, those guys are semicirculars and circulars, which are free. And we saw before that this gives us a semicircle. And this was just the idea that we realize this as a big GQE matrix, which we cut into blocks. And of course, we could take X2, write it also in this form, with semicirculars and circulars which are free from those, because this would just be taking 2 independent GUEs, cutting both of them into blocks, and then we just get this. Okay, but that's not so good, because what we have to do is we have to compress L of F2. So we also need a projection of trace 1/2, which of course in this matrix picture should of course be projection to the corner. And for this we choose the other clamp generator in a different way, which allows us to get a very canonical realization of this projection. So for X2, actually, we take a generator which is of this form, where U is a high unitary, which is free from this. Okay, we take those as free generators. So what do we have here? So S1, S2, C, and U, the 4 guys which are showed up there, they are star free. And of course, S1 and S2 are semicirculars. C is a circular, and U is a high unitary. Good. Okay. So I'm claiming that those 2 guys together generate L of F2, and why? Because I mean X1 and X2 are free. I mean X1 has a semicircle distribution, X2 has which distribution? I mean a high unitary has the uniform distribution on the circle, and here I have just 2 times the same high unitary, which means this guy, so the distribution of this guy this is a normal operator, but the distribution is, I mean, this part has the uniform distribution on the circle, and here I have twice the circle. So this means this operator has a uniform distribution, I mean, 1/2 here and 1/2 here in the complex plane. Normal operator is this distribution, so in particular it has no atoms. Having no atoms is the only important thing for seeing that if this and this are free, then actually they together generate LFF2. And so why are those guys free? I mean, this is again the idea by random matrices. This guy we approximate by a GUE, which we cut them into pieces, and this guy we approximate just by a deterministic matrix. So we just make sure that in the limit we have this distribution. But GUEs and deterministic matrices are also free. So actually I can choose here more or less what I want. Not that I choose exactly this distribution here, is just because the unitaries will be nice later. But I could take here anything which has any distribution which I like. Okay, so this means, again, I take here the deterministic matrices, which, for example, I mean, I put in here eigenvalues on this circle, and here I'm putting eigenvalues on this circle, and in the limit this will converge to this distribution. Okay, so again, this can be made precise, and actually again, you can prove this statement that those two guys are free, independent also of random matrices, just by combinatorics. But I mean, who would come up with something without having these random matrix pictures in the back of the mind? Good, okay, but so we can take this. So we know that L of F2 can be generated by those 2x2 matrices. And actually now you see that actually we have here the right freedom in the entries. So you see we should have 2x2 matrices where the entries are coming from L of F5, and we have 5 free generators. And I mean actually what do we have here? We have S1, S2, C and U. S1, S2 and U are normal. So they have just one degree of freedom. But C is a non-normal guy. It has a real and imaginary part, which are 2 free guys. So we have here actually 1, 2, you have 2 more, 4, 5. 5 free generators which generate this. So you see where the 5 comes from, because it really fits this here. So, let's see where we are. Okay, so we take this as given now, and we can think more about it, but it's a random matrix picture, it's not very hard to prove. And maybe we are down, so we x1 and x2 are now really given as 2x2 matrices over n of F5. Because the Neumann algebra, which is generated by the entries which we are using there, also by S1, S2, C, and U, is L of F5. Because the C you can split into the real and imaginary part, which are free, and then you have here 5 free guys, which are either self-adjoint or unitary. And they together give you L of F5. Good. Okay, but actually, I mean, this is not yet the proof, because we don't really know whether x1 and x2 generate all of this. So I mean, I have generators here, which are sitting here. But of course, this here tells me then, I mean, all of those guys should generate this, and this is not so clear. Okay, but I mean, it shows already that we have here chosen a good representation which fits with this statement. And now we are really going to prove in this representation, we are going to prove that this. So that if I take this and I compress it, then I get this. So, but this means essentially how do we get those guys out of x1 and x2 again? And that's what more or less we're going to do if we do those compression. Good, so now let us really do the compression. So let me denote von Neumann algebra generated by x1 and x2, let me call it n. This, of course, is the frequent factor. Because those guys are free, and each has a non-atomic distribution. Yeah. And so now what we have to do is we have to compress this now with a projection of trace 1/2. So I need a projection from somewhere. Okay. And of course, this projection should now really be the nicest projection which we have around. I have written everything in 2 by 2 matrices, so of course if I take one here and throw everywhere else, this is a projection. So that's something which I would like to get. And of course I need a projection in von Neumann algebra. I cannot just say, okay, let's take this guy here, because in general I would not know if this is von Neumann algebra or not. But if I have things written like this, then I can produce this by operators which I have. So namely, if I take now x2 star, so what is this? So this is, here I get u times u star, and here I get 2u times u star, but u is a unitary, so it's 1. So I get here 1, and here 4. Okay, not directly what I want to get rid of this 4, but now of course I have functional calculus, and of course I can take polynomials such that I get a 1 here and this goes away. I mean, the point is that I have here different thing than here, so I can separate this by polynomials. So this guy here, of course, is in my n, and this means I can also separate this, and then I get also n. Just by applying functions. A function which here is 1 and here is 0. So this means this guy here, and also the other way around, are also equal. And of course now let's say, of course, both are projections of trace 1/2, let's say I call this P. That's the projection with which I want to compress them. I call P. This is a projection of the right trace. And the projection again. N is here given, I mean, as 2 by 2 matrices over some underlying von Neumann algebras, and of course the trace in the 2 by 2 matrices is the normalized trace for the 2 by 2 matrices, tensor the trace in the underlying von Neumann algebras for the entities. So in particular, this guy here has trace 1/2, because I'm using the normalized trace for the 2 by 2 matrices. Good. So to see by which elements can I generate my von Neumann algebra. And then I want to see by which elements can I generate compression. And in the end, of course, I want, for the compression, I want to get 5 elements which are free. But let us first look at n before we compress. So we are somehow separating the different engines. So is of course generated by those two guys, but now I also have the projections, this, and this means I can multiply, of course, those guys from the left and the right with those guys. And this means if I multiply this with P and P from both sides, I setting this guys equal to 0 and I just remain this. If I multiply from one side with the 1 here, and from the other side with the 1 here, I mean I'm just keeping those guys. So this means with this multiplication, I really can just isolate each of the entries. So this means the end is generated by, okay, the first matrix. I can take this guy, the first matrix. I can take this guy, and I can take this guy. Of course, I also have the one where I have the C star here, but this is just the adjoint of this. Generated, I mean generated in the von Neumann algebra sense, which means I'm also applying the star to my elements. So those I can cut out of the first matrix, and for the second one, I can take this U here and this U here. Of course, I get a 2 here, but of course, I can just divide by 2. Okay, so I mean, those 4 elements are in N, but on the other hand, is those 4 elements, of course, I can reconstruct x1 and x2. So this means N is a priori generated by those two guys, but then it's also generated by those. Which means I have separated the entries here. Good. Okay. And this guy here I have a circular element, and this I want now to replace by its polar decomposition. That's why we talked about the polar decomposition of circular elements, because then this will allow me to replace the C by its absolute value and its polar part, which is a unitary. And this unitary will later allow me to move things around. Okay, so this guy here, instead of taking this, I take its polar decomposition. The polar decomposition of this matrix is essentially the matrix version of the polar decomposition of C. So I write this as 0, V, 0, 0 times 0, 0, 0, Q. So you see this element here is just V times Q, and V times Q is the polar decomposition of C. So C is equal to V times Q. Circular element, and for this we know exactly what this is. So namely, main point is V and Q are star free. U is a high unit, V is a high unitary, and the Q is the absolute value of a circular element, which is the quarter circular distribution. Good. Okay, and so I mean, I start with the polar decomposition of this, and then of course you see that I can write this like this, but now this here is the absolute value of this guy, and this here is a partial isometry, so this here must be the polar decomposition of this element. And this means in particular that this and this are still in N, because we know the polar decomposition happens within the von Neumann algebra. So this here is decomposition. Is the polar decomposition of this element here. Polar decomposition in von Neumann algebra N, but we know the polar decomposition. In polar decomposition, both parts are in the von Neumann algebra. So this means this and this guy are also in my von Neumann algebra. So 0, V, 0, 0, and 0, this means this guy here, I can replace by those two guys. They are also in N. So if I have those two guys, I can get this guy. If I have this guy, I also get those two guys. So I can go back and forth. So instead of using this, I can use those. Okay, and this means my phenomenon algebra N is generated by those two guys and this, and this. So, and thus, N is generated by, again, so we have as 1, 0, 0, B, 0, 0, 0, 0, Q. That's the two parts in the fuller decomposition of this. Replace this by those two, and then I have just 0, 0, 0 is 2, U 0, 0, 0, and 0, 0, 0. And so what I have here are 6 elements. Let me call them y1 and y2, y6, up to y6. And then from y1 to 2. So you see n is generated by 6 elements, which are of course not free, no? Because we have a lot of zeros here. But we still, we want to do the compression, and then we would like to see actually 5 free elements, not 6. Oh, okay, so we have to see why we get 5 and not 6. Good, so now we should go over to the compression. So this is still n, but we have now a set of generators where we have somehow separated nice guys which are free, or which we all know. Of course, they are sitting at different places in these matrices. The compression. Compression, of course, now is this projection P. It projects down everything onto the one matrices. Good, so that's N, and now we're looking on P and P. That's the compression. So P is still our projection media, is this one. Yeah, so this P and P, what is this generated? Of course, now one has to be, it's not just that I can take P times P of all those generators here, because what is P and P? This means I take a P, then I take a guy from N, but the guy from N is maybe given by products of those guys, not sums and products. And then I have a P at the end. So this is generated by, so this means I have a P at the beginning, but then I might have product of all those guys in arbitrary orders. Let's say y1 up to yn, and then I have a different P there. And of course, it's not the same as just applying P times P from both sides to each of the y's, but I want to do something like this, and I can essentially do this. I have here 1s on this side. I can write this as P, y, I1, and then I put a 1 here. And then I have 1, 2, and so on. And I put 1s in between. And this 1s I can essentially write in terms of P and another thing which I also have very nicely around. So I replace the 1. And the 1, of course, is the matrix 1, 1. But I can write this as 1, 0, 0, 0 plus 0, 0, 0, 1. And of course, this here is our matrix P. Okay. p here, or p squared if I like, and then put one p here and one p here. This is the same as p squared, but I also have a different contribution. But this I can also write in terms of things which I have here, namely exactly this partial isometry. So maybe I can write this as 0, 0, and v star 0 times 0 v 0, 0. Because, yeah, you see, when I multiply this, I will get a lot of zeros, and this one here comes because v star times v is equal to 1. V is a high unitary actually. Just a unitary is enough. Also, this guy here, I write in terms of this. And that's why I wanted this v. And that's why I did the polar decomposition for the c. I mean, the c itself, of course, I cannot use because c star times c is not 1, but something else. High unitary polar decomposition I can use. And maybe that's important here. Or this here v twiddle. And this v twiddle star. Then you see I can replace the one here either by p star, and then I can give a p to the y before and a p to the y after, and then I also get a contribution where I have a v twiddle star times a v twiddle, and of this I can give the v twiddle star to the y before and the v twiddle to the y after. So I mean I can write this as a product of things in terms of the generators, where I multiply generators, but not only by p, but also by v twiddle from one to the other side. So this means I need more space. P and P is generated by actually yi's. So yi's are now y1 up to y6, but I have to multiply them now. I can multiply them both sides by p, or I can multiply them here with a p, and here with the v star twiddle, or with the v twiddle here by p, or y twiddle yi's, and I mean, in the beginning I can multiply them with a p or v twiddle, and at the end I can multiply them with a p or a v twiddle star. And I mean, if I have all those elements, then I can generate all elements of this form. And of course, I mean, those elements are also in my fundamental p and p. Because if I multiply another p here, that's okay. Huh? I mean, yeah, those guys are good. Okay, so this means my phenomenon algebra is generated by those, and though I have to see what happens with the y1 up to y6 if I multiply them in this form. This will give me generators for the compressed algebra, and those hopefully will be free. Okay, so we have to take those and multiply them. And of course, I mean, we multiply them, of course, with the right thing. I mean, this, of course, I can multiply p and p from this side, that's okay. This guy here, of course, I should not, if I multiply this with p, it will just give 0, because p from here times p from here just picks out this entry. So this guy, with this guy, I should take this product here. So exactly one of the products from here, for each of them, will give us something. And actually what this does is really moving all the entries here exactly in the 1-1 corner. Because that's exactly, I mean, yeah. The P just checks whether I'm already in the first row or column. But this guy here, it moves things from the second row or column into the first row or column. So we have to multiply those with the right element and see what we get. So this means P and P is generated by the following guys. Okay, so this I multiply with P from both sides, but it doesn't change anything. It's S1, so. Okay, the next guy, this guy, I have to multiply, let's say, P from this side, but from this side, I have to take this guy, then I multiply with the V star, but I'm also moving the element from here to here. So what I get there is V star. The V comes from here, and the V star comes from multiplying with this guy. So what's the next? So here I have to move row and column from 2 to 1, which means I multiply from this side with the star, and from the other with the V. So this gives me VQ star. Here the same. I get V S2 V star 0 0 0. Okay, this. Now this U here, of course, I just multiply with P and P, nothing changes. So I have the U 0 0 0. And for the last guy, this guy here, I again have to move it from the 2 2 entry to the 1 1 entry by multiplying it with this from one side and this from the other side. And that's the only multiplication which produces something which is not 0. And this gives me again something like this. Okay, and so you see my compression P and P is generated by those 6 elements. And now, of course, I mean these elements here are living now on a Hilbert space which has all those many zeros. And this is, of course, I mean I should now represent my compression not on the original Hilbert space, but on the subspace on which P projects. But this is exactly the 1 1 entry of all those matrices. And you see, I mean, that's exactly what the compression is doing. It's just looking on the 1 1 entries of all my guys. And so this means if I restrict this now really Hilbert space, where I should look on this, P and P is exactly generated by all the entries of the 1 1 entry of all those matrices. P and P is generated by, so I just take those guys. So as 1, I have V times V star, V Q, V star, V S2, V star, U, and V star. Okay, you see we still have 6 elements, but of course I mean, one of them is not very interesting because V is a high unitary, so V star is just 1. So we can forget about this. So this is just 1, and then we have just left these 5 other elements, and now I'm just claiming those 5 elements are really free. And each of them, of course, has a non-atomic distribution, so this tells us what we get is element. Each of the 5 elements as 1, the ones like this one, V, Q, V star, V, S2, V star, U, and VU, V star, each of those guys. Let's first look on distribution. So I mean they are all normal elements. This is self-adjoint, this is self-adjoint, this is self-adjoint, this is a unitary, and this is also unitary. So they are all normal. and they all have a non-atomic distribution. I mean, this is a semicircular distribution, this is a quarter-circular, semicircular, a high unitary, and a high unitary distribution. So all of them are normal and hence non-atomic distribution. And of course now the main point is that those guys are free. But that's indeed the case. This distribution. And furthermore, they are star-free. Yeah, like this. So what do we have? Essentially, I mean, we have two groups of elements. I mean, we have here guys which are somehow conjugated by the V and the V star, and then we have the other ones. And I mean, conjugating by a free high unitary. And the V here is free from the other guys which we have. So we have here a group of elements, namely Q, S2, and U, which are conjugated by the V star. And we have here S1 and the U. And then first of all, I mean, this V is free from what I have here and what I have here. And then conjugating by V makes the guys free. I mean, even the U here and the U here, if I conjugate it here by the V star, it's made free. So the V U V star is free from this U. And in the same way, I mean, those group here is free from this, but also inside the groups I have three elements. And those guys are free, and also those guys are free. And this means I have everything is free. So I really have here 5 free elements. This is then the conclusion. So our compression P is generated by 5 star-free elements. Non-atomic distribution. That's something which you have seen earlier, that those such guys generate the free group factor of 5 elements, 5 generators. So that's what we line. Again, P is really isomorphic to the number 5. Good. Okay, so this is, I think, a very nice and quite non-trivial application of free probability to seeing the structure of the free group factors. Of course, I mean, so what does this now really tell us? Huh? I mean, first of all, it doesn't tell us whether the free group factors are isomorphic or not. It just relates some of them via compression. So let's see what we can get out of this. Okay, so first of all, as I said before, I mean, I did it for this very special case, n and k is equal to 2, but it works for all n and k, original group of all the rest. So the same proof. I mean, then you just take, I mean, you always take one element of this form, and all the other ones, generators, you realize in this form. And then you do the same, so the same proof. Yes. Also for general n and k. And actually, okay, I mean, the proof we are doing here, the original proof of Roland does not work for n equal to infinity, but this can be done, and then it's actually still true if you read the formula in the right way, that then m is also equal to infinity. So in particular, it says if we have a compression of L of f infinity, we just get L of f infinity again. So I mean, generally it says if I compress a free group, I get a free group with another number of generators. But if my numbers of generators are infinity, then it stays infinity. And this means in this case, at least we get something about the fundamental group. This also true and equal to infinity. Then it says, if I take the free group factor on infinitely many generators, compress it with a trace, with a projection of trace 1 over k, then I just get again the free group on infinitely many generators. Okay, so this means after compression with those guys, I have the same free group factor, which means that those guys are in the fundamental group. This means, of course, all of Q. All rational numbers are there. So this means Q plus is a subset of f infinity. Okay, and if n is not infinity, of course we cannot make a direct statement about the free group, about the fundamental group, because we do not. I mean, we get after compression, we get another free group with another number of generators, but we don't know whether this is isomorphic or not to the original one. So this means we cannot get a conclusion. So n less than infinity, we do not get a direct consequence for the free group, the fundamental group of L of Fn. Since we do not know whether the free group factors of different numbers of generators are isomorphic or not. But at least we can get something out of it. So namely since we can connect things via compression, this means if we know some isomorphism between the free group factors, by compression we get other ones. There's no direct consequence, since we do not know whether different L of Fn are isomorphic or not. Okay, but on the positive side, compression results show us something. Compression results show that if I have some isomorphisms between the three group factors, then this implies others. So shows that some isomorphisms imply other isomorphisms. So for example, I mean, assume we would know that the free group factor on 2 generators and the one on 5 generators are isomorphic. Oh no, let's say 1 and 3. So we would know that L of F2 is isomorphic to L of F5, which we still don't know. But assume we would know this, then of course I can prove the compression of this isomorphism, and this gives me something else. So let's say I compress this with a projection of trace 1/2, then of course this tells me that after this compression it's still must be isomorphic. Okay, but we know what those compressions are, namely there are other free group factors. So namely this one here, that's what we just calculated, was proof that this is the same as N of F5, and if I compress N of, no, I want here, let's say, okay, so 2 and 3 are the same. Then after the compression they also must be the same. The compression of F2 gives me N of F5, and the compression of N of F3 gives me N of F9. So this means if I would know that N of F2 and N of F3 are isomorphic, then also N of F5 and N of F9 must be isomorphic. Okay, and this, I mean, I can draw compressions, and this means one isomorphism implies a lot of other isomorphisms. And actually, one can define this whole thing. I mean, this is a little bit restricted because I can only do compressions with 1 over k, only with the rational numbers. But actually, one can refine it and also do compressions with t, and then one gets here on the other side, one gets something. Okay, I mean for n, not for infinity. One gets something which would have a non-integer number here, which a priori is not defined. But this can be defined, and this was done by Roland and by Dykema, and this means in the end one can connect all free group factors with any other free group factor by compression. And this means if I have one isomorphism between two of them, then I have isomorphisms between all of them. And this in the end means there are only two possibilities, namely either all of them are isomorphic or they are pairwise or non-isomorphic. So this is quite something more than. Okay, so a refinement of this, and this also then means that one defines L of Fn not only for integer n, but also for arbitrary real n. But one has to show that this can be done in a consistent way, so I don't know how to do this. But in the end, then using this machinery and results shows that one has the following dichotomy. There are only two possibilities. Either all of them are isomorphic, or they are all different. We only have one free group factor, or we have really many of them. So we're going to get so maybe the final theorem of this, also which was done by Dykema and Roland independently around 1994. Of course, building on this important, especially cases of Golescu, was that we have only two possibilities. So we have exactly one of the following possibilities. So the first case is that all free group factors are isomorphic. So all, and this includes also the interpolating ones. Free group factors are isomorphic. So this means L of Fr is isomorphic to L of Fs for all possible choices of I and S bigger than 0 and bigger than 1, and also including infinity. For all 1 even less. Of course, L of F1 is just the commutative factor, so that's different from the others. But here, all of them are isomorphic. I and S can here be real numbers. Okay, we don't really know what interpolating ones are, but still, I mean, even for integers, one it's a quite strong thing. So for all those guys, and in this case, then we know that the fundamental group of all of them is just out of R plus. Because this means I mean, if I take a compression of one of them, I get a free group factor, but if they are all isomorphic, then it's isomorphic to the original one. So in this case, free group factor, the fundamental group of each of them is maximal possible R plus for all choices of R. Okay, or the other extreme which can happen, the only other possibility is that all of them are pairwise non-isomorphic. So this also includes the interpolating ones. So free group factors are pairwise non-isomorphic. So it means whenever I have two of them, let's say on R generators and on S generators, then they are non-isomorphic if R is not the same as S. And then this is for all possible choices R and S. It's different between infinity and infinity is included again. Okay, and in this case, if they are all isomorphic, then for the fundamental group, we have the other extreme, namely that it's only the smallest one. In the case of a finite number of generators. In the case of an infinite number of generators, we know by the result of Roland Speicher extension that the fundamental group is always the maximum one. So this for R equal to infinity, this is always true. But it doesn't tell us whether guys are isomorphic or not, because compressions of F infinity only gives us, again, F infinity. Only the finite number of generators, there we can connect different ones. Okay, and if they are all non-isomorphic, then in this case we have the fundamental group of all of them, different from infinity. It's just the smallest possible case, which just consists of one, the smallest possible subgroup of R plus, which means, I mean, okay, there's no way of doing a compression and get the same phenomenon algebra again. But this is for all R not included. Okay, so that's one of the first big successes of free probability theory for the application to von Neumann algebras. Yeah, so we know quite a bit more on the free group factors. I mean, in the beginning, it would have been possible that some of them are isomorphic and some of them are not isomorphic. But now of course, we know it's much more homogeneous. So either all of them are the same or they are all different. Okay, we still don't know which of the two cases is. Good. So we have one more lecture, and I want to say a little bit more, maybe about the other successes of free probability for dealing with von Neumann algebras. And this goes a little bit more in the direction of free entropy and such stuff. So I want to give you some general idea of this. Free entropy is another big topic in free probability theory, which again is motivated by this idea that von Neumann algebras can be approximated by random matrices. Okay, and the general idea, I mean, is somehow we have von Neumann algebras operate over the Hilbert space, but we can approximate them by matrices. And actually, we have many matrices. Okay, and this means that hopefully properties which we know for matrices survive, at least some of them, in a limit. That we can transport something which we know about matrices to the limit. Of course, I mean, about matrices we know more or less everything, and in the infinite dimensional setting, there are a lot of things which are not true, or things which are different from the finite dimensional setting. But I mean, at least some things, non-obvious things, might go over to the limit. And one other big result of what we lesson, for example, was that the free group factors don't have a Cartan subalgebra. And this was a big open problem for quite a while. And I mean, this idea is coming from free probability theory. He could show that they don't have this property. And so next time I want to give you at least some idea